So the next half of today's lesson is dealing with the application part of logarithmic exponential equations. Like I said before, there really isn't much, or really not too many problems that do have logarithmic functions involved. If they do, the equation is going to be given to you, okay? If they do, it's going to be given to you. But a lot of times, a lot of real world situations are modeled with exponential functions because exponential growth and exponential decay, okay? A little bit of background with that. When they're talking about like a population increase or like a virus or a plague or something like that, they'll say that, the numbers are growing exponentially. They're talking about an exponential growth function in which the graph is continuing to increase as x gets bigger, which usually represents time. The number of people are also increasing, or the number of people dying are also increasing if it's a virus or something like that, okay? Then you have exponential decay occurs when a quantity decreases by a certain rate over time, okay? So certain things that can model exponential decay would be car value. Trying to think another example of exponential decay. Population of an endangered species, for example. Okay, those are all examples of exponential growth and exponential decay. Okay, so everybody understand the difference between the two? We've graphed these. Okay, growth is going up, decay is going down. All right, and these right here are the two formulas that we're going to use to represent these exponential growth and exponential decay word problems as we write them, okay? You are going to end up having to write a majority of these equations, and so this is the format in which you write it in, where y represents the final amount. It is known as the dependent variable. So after a certain number of years, what is going to be the value of the car? Okay, if it's depreciating, how much is it going to be after 10 years or something like that? Okay. A represents the original amount. A is also the y-intercept of these exponential equations. Okay. So if I buy a car at $25,000, that is the value of A, because that's how much I paid for the car. Does that make sense? Okay. R represents the rate of decay or growth as a decimal. Okay, so let's say that the value of the car is depreciating 8% every year. Then our rate would be what? 0.08, because it has to be converted into a decimal. Don't be confused by problems like this that say the rate is 0.6%. Yes, that's a decimal, but this is still a percentage. So how would you represent 0.6% as a decimal? 0.006, okay? That's usually a common error that a lot of students make when they get to these types of problems. And then, of course, t is represented in time, normally by years, okay? Normally in years. So then if it asks you, what's the value of a car after 9 months, what would you plug in for t? 9.9. 9 months is how much of the 9 over 12, which is what? What's 9 divided by 12? 3/4, which is 0.75. So you want to always make sure that your time is usually in years, okay? So that's the general makeup of these types of problems, okay? Is everyone good? All right, let's look at some examples. I do have a sheet for you that I just printed out, so let me go grab it, and we're going to look at some of these examples simultaneously. So here's an example. It says a typical cup of coffee contains 100 milligrams of caffeine, and every hour approximately 16% of the caffeine in the body is metabolized and eliminated. Let C represent the amount of caffeine in the body in milligrams, and T represent the number of hours since the cup of coffee was consumed. Write C as a function of T. You have to write out this equation. Now, first of all, C as a function of T. Are they using X and Y? No. What's going to represent X in this problem? C. Yeah, what? What's going to represent X? T, because usually X is the independent variable. That's the thing that's going to happen regardless. Time is going to happen regardless. But C is going to be your dependent variable. So that's going to represent Y, because it represents the amount of caffeine in the body, okay, as time goes forward. So we can already kind of set this up a little bit as C equals blank value for A, 1 plus blank value for our rate to the T power, okay? That is key, especially if it says write C as a function of T, okay? So far, so good. Now, what does the A in this problem represent? The starting amount, which is how much? 100. So then this is going to go in for our A. What is our R? 0.16, because it says approximately 16% of the caffeine in the body is metabolized and eliminated. Now, I had to go back through and I had to make sure to double check, because even though I read the problem, I wanted to double check. Is this a growth or is this a decay problem? How do you know? What eliminated, right? Which means that it's no more. So it's decreasing. It wouldn't be plus, because that means it would be increasing, right? You can't really eliminate something and keep going. So then this needs to be a minus. I originally put a plus and I was like, ooh, let me not do that. It's actually a minus. Okay? Now, can we do 1 minus 0.16? What is that? 0.84 to the T. So our equation, our C as a function of T, is C equals 100.84 to the T. This is the equation that can help us figure out exactly how much caffeine is in the body after a certain number of hours. Okay? And it just so happens it asks us how much caffeine is in the body after 5 hours. I got to plug in 5 for T. So this becomes C equals 100.84 to the 5th power. Okay? That's why I asked you guys to get your calculators, because these types of problems, yes, they are done using a calculator. Okay? So we go in and we type this in and we figure out how much caffeine is in the body after 5 hours. What did you guys get? 41.82. Now, how should we round? 3 significant figures. So it's going to be 41.8 milligrams, because this is a word problem, so we need to make sure that we include our units. Okay? Questions? So the main thing is we want to figure out which equation it is, either growth or decay. Make sure we find out our pieces and we plug in, okay? Let's look at the next one. Okay? The population of a city is given to you. It's not given on your paper, so you need to write it down. T equals 105,300 E to the 0.015 T. Please make sure you write down that equation is not written on your paper. You need to write it down. Where T equals 0 represents 2,000. According to this model, when will the population reach 150,000 people? Yes? The exponent is a 0.015 T. Okay? In this particular problem, what variable am I looking for? I'm looking for my T, because it says when will this population reach that amount? When refers to a time. So I'm looking for T. I'm looking for an exponent, which means I'm going to need to solve an exponential equation, which is what we did last week. Okay? What does the 150,000 represent? Population, the p-value. Okay? The population at a certain year in which it reached that much. So I'm going to set this equation equal to 150,000. And now it's a matter of solving this exponential equation. Now, on Friday, this is what you guys should have done a few of these types of problems that did involve the E. Okay? Now remember, talked about this last week. E represents a specific exponential, or a specific number, but it's an exponential equation still. So usually the steps are you isolate the exponential part, then you take the log or the ln to solve for your variable. Those were your 3 steps. How do I start with solving this problem? I need to divide by what? Mumble, 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 mumble. Yes, I need to divide there. And I do understand that this is probably some nasty decimal. Am I right or am I right? Okay, it's not pretty. Now, the one thing you don't want to do is you do not want to round that decimal and then continue to solve this problem, because you're just going to continue to get further and further away from the most accurate answer. Okay? So, going to do a lot of stuff written before we actually go to our calculator. Okay? So now I have this number equals e to the 0.015t. What do I do at this point? I got to do the arrow, the loop. Okay? If I do that, what do I need as well? I need a ln. I need an ln. ln goes specifically with e. If you try to take the log, I don't think you can. So you do the ln. E and ln always go together. So step 2, I need to take the ln of both sides. So this becomes ln of this entire fraction. And when I take the ln over here, what happens to the exponent? What happens to this part right here? It moves to the front. It moves to the front. That's why we take the log of both sides, because then it will allow us to apply the power rule that allows us to bring exponents to the front. And then I heard someone say it, something about ln and e. They cancel out. So then that is gone. And so the last thing I need to do to solve for t is what? I need to divide. So what I'm ending up typing in my calculator is this left side right here, the ln of this fraction divided by 0.015. Only on the right side, because it has the e that's attached to it. But on the left side, the ln is being applied to this decimal here. Okay? So you're going to type this in. If you need to do it in pieces, that's fine. But we're looking to figure out the value of t, and then we'll answer the question. Compare your answer with your neighbor. Make sure you're rounding to 3 significant figures. The ln of that number. Make sure you're careful on how you're typing this in. You need to do the parenthesis fraction. Then you need to do the ln, and then divide by 0.015 if you're using those these scientific calculators. Who got an answer? Okay. Olivia, what did you get? 23.6? Should be 23.6. Okay? 23.6 years later is when the population is going to reach 150,000. Okay? What year is that? It's going to be, I'm going to take the year 2000, which represents 0, year 0. And then I need to add 23.6 years to it. So then that's going to be 2023.6. So about a little bit over halfway through the year of 2023. So that's going to be 2024. Questions? That year answer is your answer because I asked you for when. Okay, so that corresponds to a particular year. All right. This particular problem, it says at the beginning of an experiment, a culture contains 1,000 bacteria. After 5 hours, there is a certain number of bacteria. Assuming that the bacteria grows exponentially, how many bacteria will there be after 24 hours? How many bacteria will there be after 24 hours? Okay? What do we know? It's exponential growth. So that means we're dealing with the equation. Is it A equals Y equals? What is it? It's A. Okay. Yes? Okay. So, excuse me, Ms. Anderson? Yes. Do you have Elvin in class? Yes. PC, send him the tennis strip, please. Sure. Wait, who? No, I know. But who? Okay. Yeah, come back. Okay. I have to cut that out the video. All right. So now that we know it's growth, where do we start? Plugging numbers I have. What's one thing? My total is Y, 7,600. Okay. My A is 1,000. And my T is 5. What's my R? Huh? That's what we're looking for? Okay. Well, not quite. That's not what I'm looking for, but I need it to figure out how many bacteria there will be after 24 hours, right? Okay. So here, I need to solve for R. What would I do? Divide by 1,000, because I'm trying to isolate my variable. This actually is an okay number. What is it? 7.6 equals 1 plus R to the 5th power. How do I get rid of that 5th power? I do what? I need to do the 5th root. Okay? I need to do the 5th root of both sides. Now in your calculator, oh, what'd you say? Oh, I click on the YX and I do 1/5. Oh. Oh, I can do second? Is this normal or do I gotta do extra things? Hate these calculators. You get the cream of the crop if you go IB. Let you know that. It's like half and half, depending on which course you go. All right, so I need to do fifth root, okay? I need to do fifth root. How do you do this? And then you put 5. Okay, so to do fifth root in those calculators, we got to type in 7.6, click the second button, and then click the Y to the X button, and then type in 5. Y to the X is a button below off. So it becomes 1.50. 0 is that significant figure now that it follows. And then I just have to do what to find R? Subtract 1. So my rate is 0.5. And now I can use that to figure out how many bacteria there'll be after 24 hours. And so then I plug in 24 for my X. Go ahead and type that in. So you probably think you have to do in that second this data in the second 7.6. There you go. Did we get an answer? Okay. How many is there? It's a big number. Did you get 1, 6, 834? Well, 112? Awesome. And we would keep it at the 2 because we can't make up for that 0.8 of bacteria that doesn't exist. So we round down. Okay? Questions? I think there's one more that deals with this particular type of concept that I want to do, and then we'll stop there. And we're still doing word problems for the rest. Like, we'll do word problems on Thursday. Okay? All right. Last one for today. So I think it's on the back. Yes? Okay. It's on the back. Suppose the experimental population of fruit flies increases according to the law of exponential growth. Growth, which means it says there are 100 flies after the second day of the experiment and 300 flies after the fourth day of the experiment. How many flies were in the original population? I know two pieces of information, or two sets of pieces of information. There were 100 flies after the second day of the experiment and 300 flies after the fourth day of the experiment. R is equal 100. But it's growing exponentially. You said 100 equals what? 100 equals A? What, you don't know your original population and you don't know your rate. But what you can do is you can set 100, which is how many flies you have after the... We could do that. We could do that. I was about to have y'all doing something completely... Not hard, but it's an older concept. Thank you for getting the door. Okay? If I temporarily make this the first day, that means that this would be on what day? The third day. So now I can plug in 300 for Y. I'm looking for, nope, I have A. Because if this is the second day, if I temporarily make it the first day, I'm going back a day. So then my fourth day will have to go back a day as well. We use this skill in arithmetic and geometric sequences and series. Okay? So 100 is going to be my initial, just temporarily. 1 plus R, which I'm still looking for. And what's going to be T? It's 3. Because remember, we temporarily made 100 our first. And then 300 our third. I need to solve. What do? Divide by 100. That becomes 3. What do I need to do? Take the cube root. And then once I get the cube root of 3, I need to do what? Subtract 1. What's my R? Okay. So now that I know my rate, I'm going to go back to normal. Okay. And I'm going to use either the 100 flies on the second day or the 300 flies on the fourth day. Tell me find my initial population. I'm going to use 100 because that's a smaller number. 1 plus my rate. And if I use 100, what do I plug in for T? 2. So I'm going to go back and add 1 to my answer. I'm going to square it. What do you get? 2.08. Because we can either use 100 flies on the second day or 300 flies on the fourth day to help us figure out our initial amount. So either one we could have used. So basically, after we figure out our rate, all that temporary stuff is done with. We go back to the original numbers. How do I solve for A? And so 100 divided by 2.08 is 48.1 about. But we are talking about fruit flies. Can we have a fraction of a fruit fly? So this is going to be 48 because we cannot make up for that 9/10 of a fly that doesn't exist. Okay?